formula for the electric field of a ring of charge is equals to E equals to kqx over open parenthesis x squared plus a squared close parenthesis to the power of 3/2. Where did this formula come from? Suppose you are given a uniformly charged ring-shaped conductor whose radius is a. How would you solve the electric field at a distance x from the center of the ring? One way to tackle this problem is to take a point in the ring dq and suppose that its distance from the point P is r. From here, we could go back to the formula of electric field E for a point charge where E equals kq over r squared. Since we are given dq, we can translate the formula into dE equals k dq over r squared. We know from the Pythagorean theorem that r squared is equals to x squared plus a squared. So we now substitute it directly to our equation and get dE equals k dq over x squared plus a squared. However, if you look at it closely, the equation we got is the electric field exerted on the point only by that small section on the ring. So we could break it down to its components, and as we analyze this, we could see that if the opposite section in the ring is chosen, it would exert a similar force. We could also break that force down to its components, and as we can see, the force in the y direction gets cancelled, while the force in the x direction adds up. From this, we could infer that the electric field the ring will have on the point P will be the total of only all the x components of the sections in the ring. So we will now be solving for dEx. Now, let's go back to the one section we've chosen. Let the angle between x and r be denoted as alpha. We know that alpha would also be the angle between DE and its x component DEx. Now, in order to get the value of DEx, we have to multiply DE with cosine alpha. We'll use cosine since we are looking for the side adjacent to the angle. Now, we'll get the equation dEx equals cosine alpha dE. Recall that dE equals k dq over x squared plus a squared. So if we substitute that, we'll get dEx equals cosine alpha k dq over x squared plus a squared. In reference to SOHCAHTOA, we know that cosine alpha equals side adjacent to alpha over hypotenuse equals x over r and equals x over open parenthesis x squared plus a squared close parenthesis to the power of 1/2. And we can now use that in our equation. From dEx equals cosine alpha times k dq over x squared plus a squared, we'll get dEx equals x over open parenthesis x squared plus a squared over 1/2 times k dq over x squared plus a squared. Let's focus on the equation for now. So far, we have dEx equals x over open parenthesis x squared plus a squared close parenthesis to the power of 1/2 times k dq over x squared plus a squared. And we can further simplify that into dEx equals kx dq over open parenthesis x squared plus a squared close parenthesis to the power of 3/2 Now, we'll integrate the equation to get Ex. The integral of dEx equals the integral of kx dq over open parenthesis x squared plus a squared close parenthesis to the power of 3 halves. We can bring out the constants, and since the integral of dEx and the integral of dq are equal to the Ex and q respectively, our final equation would be Ex equals kqx over open parenthesis x squared plus a squared close parenthesis to the power of 3 halves, which is just the equation that we saw earlier. Now, to go back to the problem, we know that the electric field in the y direction is cancelled out, so we can now denote that E is simply equal to Ex. Thus, the equation for the electric field of a ring or charge is E equals kqx over open parenthesis x squared plus a squared close parenthesis to the power of 3 halves. Now, what would happen to the electric field if the point P is in a distance 0 from the ring or is in exactly the center of the ring of charge? To answer that, we can just look at the equation and see that the numerator kqx will become 0 if x is 0. Therefore, the E at the center of the ring is simply equals to 0. Another way to analyze this is to draw the ring, and you'll see that the components of the force from different sections of the ring will only cancel each other out, leaving a total electric field of 0. But what would happen to the electric field if the point P is in a distance x so far from the ring, or if the radius A of the ring is small? To answer that, we can just look at the equation. And from there, we can disregard the value of A since it's small. And so the denominator will become x squared to the power of 3 halves, which is equals to x cubed. From here, our equation will look like kqx over x cubed, which could be simplified into kq over x squared. Doesn't this equal look familiar to you? It is the same the equation we have for the electric field of a point charge, which makes sense because when the point is far and the radius is small, the ring of charge would basically look like a point. Don't believe me? Why don't you try and draw it? A charge of 5 nanocoulomb is spread uniformly over the surface of a non-conducting ring of radius 1 cm. Find the magnitude and direction of the electric field this ring produces at a point P on the axis of the disk at a distance of 2 cm from its center. We can approach this problem by first listing down all the given values. Q equals 5 times 10 to the negative 9 coulomb, A equals 1 centimeter or equals to 0.01 meter, X equals 2 centimeter or equals to 0.02 meter. Notice that we already have all the variables we need to be able to solve the problem, so we can go ahead and plug them in.